Sumio Iijima, who is first accredited to discovering carbon nanotubes, many other people had observed them before, but they never presented them with enough context to be considered a fleshed out discovery. Sumio Iijima, he developed the electron microscope used to view these atomic structures as early as when he was an undergraduate student, and he spent years researching them and piecing together enough information, background information, to say what carbon nanotubes really are. So this expansion sparked a global interest in the field of nanomaterials and opened doors for new discoveries in nanophysics. So as for how a carbon nanotube is made, this hexagonal sheet is a carbon material called graphene. It's a two-dimensional material, meaning it's only an atom thick, so its z-dimension can be approximated as 0. And these vectors drawn on the top are the direction along which you cut and roll the sheet. And that determines its chirality, which can kind of be shown here. So my hands are chiral. If I turn my left hand around, it doesn't match up with my right hand. And if I took a mirror image of my left hand, it would just become my right hand. It wouldn't be itself anymore. So they can't be mapped to their mirror images. So my hands are both chiral, and they have different chiralities or configurations. And these two vectors, the armchair and zigzag vector, are special in that they make achiral tubes, which are tubes that can be matched to their mirror or mapped to their mirror image. And any vector that's not one of those special tubes, so anything in here, is a chiral vector, which makes a more messy looking tube that could not be mapped to its mirror image. Expanding more on these configurations, each row of red hexagons shows the direction along which the tube was cut and rolled, just to give you a better image of the vector versus the tube it makes. And this is an armchair vector, and these two are both zigzag vectors. And this is a guide to the reciprocal space, where the red hexagon is the Brillouin zone, and that's a tough pronunciation for me, so I'm just going to call them hexagons. And in the blue is electric state lines, which correspond to energy levels. And so this tube is a metallic tube because the flat edge of the hexagon aligns with the state lines. And these two are both semiconductive due to the way the sharp edge points to the state lines. And because this edge is touching it, whereas this one misses the state line, this tube has a lower band gap than this one. So because of their unique properties, carbon nanotubes have a very wide array of uses. Because of their convenient tube shape, they can be used as delivery docks for drug delivery, for cancer treatments, and because of their very high tensile strength, they could be used to make bulletproof vests. And because of that tensile strength, in addition to their low density, they could be used to make heavy-duty, lightweight gas storage containers. And because they are transparent to visible light and highly conductive, you can see through them, while they can pick up the heat of your fingers, so they could be used to make touchscreens. And the use I'll be looking into is lithium-ion batteries. So what are lithium-ion batteries and how do they work? Well, they have a cathode and they have an anode. These are flipped inconveniently. And the cathode and the anode, they are both able to store positively charged lithium ions. And then there's an electrolyte separator in between them through which the ions can travel. And as the lithium ions move, they generate free electrons that can't go through this barrier. So they get grabbed up by the current collectors and they go overhead in the form of electron current, which you can either discharge it to power a light bulb or something, or you can send them backwards to charge it using like another circuit. So you may, the cathodes are typically made of lithium cobalt oxide, and the anodes are typically made of some carbon material like graphite. And that's where our carbon nanotubes come in. So you may be thinking, why bother looking at carbon nanotubes if graphite is an option? So this is a table that compares some of the information about them. Single-walled carbon nanotubes and multi-walled carbon nanotubes both have much lower density than graphite, so they could make for a lighter battery. The elastic modulus is about the same for single-walled and graphite, so I guess that rules out multi-walled, so we would just be looking at single-walled for our purposes. And as far as strength goes, it can range from 50 to 500 gigapascals, whereas graphite is capped at 130. So this could make the battery not only lighter, but also much stronger than one that's using graphite as the anode. Resistivity, it can range from 5 to 50. So in a good case, it would be lower, and that means that the electrons have to fight against less resistance in order to get through. So that can make it work smoother. And the thermal conductivity is theoretically about the same, but thermal expansion theoretically is negligible for single-walled carbon nanotubes, which would be a factor that we wouldn't have to think about when we're making these batteries. So that would just make it more simple, because with graphite you have to consider that it expands when it gets hot. And then thermal stability, single-walled carbon nanotubes have much higher thermal stability than that of graphite, which is always a good thing to have when you're working with electronics. So one of the ways, the purpose of the anode is to hold on to the lithium ions, and one of the ways that it can do that is through intercalation. These red rings represent a defect of n amount of bonds, and this yellow worm-looking thing is actually the path that a lithium ion would take, where it begins at green and travels through yellow. So with no defects, it just bounces right off. With a 7 bond wide defect, it gets in a little bit, but gets bounced. With 8 wide, it still gets bounced. But with a 9 bond wide defect, it's able to get in there, and the carbon nanotube can hold on to the lithium. But a better way that it can do that is by alloying extra metals on. And this is a visual for what that process would look like. This shows gold, golden nickel, and just a nickel. And this is the atom density as you go down the z-axis. And these are taken over time, so how the system kind of settles itself out. And the little red bonds are extra carbon bonds that act as kind of like the glue that holds it together. And a way in which carbon nanotubes are better than graphite for this purpose is that they have like they can make a flexible mesh material that could handle more strain, and it would be able to endure the change in volume that you would have when you alloy extra metals in there. And this is a forest configuration of growing the carbon nanotubes, and this, I don't know what it's called, I think it's just what they naturally want to be like. But this way is much harder to grow than this one. So this is what you would see more often than this. And you could grow them longer like this than you could if you were trying to grow it like a forest. So this is some data that goes to show that adding carbon nanotubes into the anode does actually improve its stats. This is the reversible capacity, which is its ability to discharge and recharge. And just carbon nanotubes is at the bottom. And then antimony, it starts up high, but it dips really low. And then tin antimonide also dips. And these two, this is antimony with carbon nanotubes alloyed in, and this is tin antimonide with them added. And both of these endured after 30 cycles. They're doing much better than the materials with no carbon nanotubes involved. And this plot is a Nyquist plot, which plots the real and imaginary component of the impedance as you increase the frequency in this direction. And this is a material of silicon, graphite, and carbon nanotubes, and this one is just the silicon and graphite. And the smaller semicircle represents a lower resistivity. So adding the carbon nanotubes in lowered the resistivity so the electrons can flow smoother. For my conclusions, carbon nanotubes have potential to become the next mainstream anode in lithium-ion batteries due to low density, high tensile strength, low resistivity, and thermal and structural stability. And here are my references.
Thank you. Any questions?
So why haven't they yet?
Because they haven't been able to grow them very long. I read online that the cap is about 2 centimeters, but I actually found an article that said with a new method, they were able to grow one up to 14 centimeters in 2020. So I think we're getting there, but so far we haven't quite nailed it down yet. So this is theoretical right now.
I have a question. What is the difference between single-walled nanotube and multi-walled nanotube?
So I can trace it out for you. So this is just a single-walled nanotube. And if there was another one around it that was a coaxial, so they have the same central axis, then that would be 2 walls, and then we could have 3 walls, and as many as you want. But I just looked into single-walled nanotubes because the stats looked better, and I could find more pictures that involved them.
Thank you. Any other questions? Okay, thank you, Amaya. Next, our presenter will be